Hello! In today's video, we'll be talking about gravity, the force that brings us all together. So you've definitely heard of gravity before, but when we talk about gravitational force, what do we really mean? You probably think of gravity as the reason why when you drop something, it falls to the floor, or if you jump up, you come right back down. But gravity is the universal force of attraction between all objects. So we know that gravity pulls us back down to the ground, but let's break down this definition to truly understand how gravity works. So we see here that it says it is the universal force. The word universal means everywhere, the whole universe. So this tells us that gravity actually acts everywhere in the universe. Now this might be contrary to something that you've heard in the past, because we oftentimes say that in space there's no gravity, but that's actually not true, because we know that gravity is a universal force, meaning that though its power or its force can change based on location, it acts everywhere in the universe. Second thing that we see in this definition is that it's the force of attraction between two objects. So two things we want to make sure we understand here. Number one, it tells us that it is an attractive force. That means that gravity can only attract objects towards each other. Gravity can never push objects apart. For example, when you jump up, the earth is pulling you or attracting you towards it. Nothing is pushing you away. The second piece there is that it tells us it's the force of attraction between all objects. We certainly do not observe or think about all objects in the universe having gravitational pull, because we're only being attracted to one object. However, we now should note that all objects in the universe exert a gravitational force on all other objects. That's right, you have a gravitational pull. So that leads us to a pretty obvious question here. If I'm telling you that all objects have a gravitational pull, why is it that all objects are not attracting other objects? Why am I only getting pulled towards the earth? Why am I not able to, like the force, pull or attract objects toward me? Well, that will lead us to a very important concept, which is the two factors that affect the strength of a gravitational force. So if you said to me, all objects are not attracting me, only the earth is, you would be right. That does not mean, however, that all objects are not trying to attract you or are not pulling on you. Let's talk about why it is that I'm only being able to experience the gravitational force of the earth. The big reason here is that one of the two factors affecting the strength of a gravitational force is mass. One thing that we can notice about the earth compared to all of the other objects on it is that the mass of the earth is far greater than any other object. For that reason, we experience the gravitational pull of the earth. We know that the greater the mass of an object, the greater the strength of its gravitational pull. So although, like I told you, you do have a gravitational pull, it is just so weak and diminutive and negligible that it's not actually able to attract anything. It's pulling, but it's not able to attract anything because the mass is so small that the gravitational force is not actually being experienced. So, the Earth, having a much larger mass than anything else in its vicinity, has the greatest gravitational pull. Hence, when that apple drops from the tree, or when I jump up off the ground, eventually I'm coming straight back down towards the center of the Earth. The second factor that affects gravitational force is distance. Now, this might become a little bit more obvious if you think about space travel or orbiting around the solar system. So we also know the distance affects gravitational force. By the closer two objects are, the greater the strength of the gravitational pull between them. So the best way I like to explain this is thinking about a satellite or any sort of space traveling object like a rocket or the space shuttle. Now, if we think about it, we're going to shoot off a rocket away from Earth using a whole lot of force, and eventually that object is going to leave the Earth's atmosphere and go farther and farther and farther away from the Earth. As that object goes farther away from the Earth, the gravitational pull between the Earth and that object become lesser or weaker. For that reason, it's allowed to leave and go towards whatever object it's looking to orbit. So for example, if I were launching a satellite to orbit around Mars, as that satellite got closer to Mars, the gravitational pull between them would become greater until eventually that object were pulled in by the gravitational pull of Mars and began orbiting around it. The closer two objects are, the greater the strength of the pull, and the further they are, the weaker. Now let's talk about measuring gravitational force. So when we talk about gravitational force, we're actually just talking about weight. So weight is actually a measurement of gravitational force, or how strongly an object is being pulled by gravity. In order to calculate this, we use the formula W, or weight, equals mg. M stands for the mass of the object, and G stands for something called acceleration due to gravity, which we will talk in much more detail about in the next video. Now, acceleration due to gravity can change based on the planet you are on. So on Earth, there is a given acceleration due to gravity, which is equal to 9.8 meters per second squared. You'll want to memorize that number. Now, if I go to another planet or location within the solar system, the G, or the acceleration due to gravity, is different. For that reason, weight can depend on two things. Number one, the acceleration due to gravity in the location that the object is located. If I'm on Earth, it's 9.8. If I go to Mars, it's a different value. The second thing that weight is dependent on, or the force of gravity on an object, is of course the object's mass. So this is pretty obvious, but you weigh more than an apple because you have a greater mass than the apple. Therefore, gravity is actually pulling on you harder than it is on the apple. That means that you will definitely, if you jump on a scale, weigh more than the apple. Now let's look at a couple examples to make that weight concept sort of make a little bit more sense. So first, let's think about the Perseverance rover on the surface of Earth. So before it got launched out into space to rove Mars for signs of life. So the mass of the Perseverance rover is 1,025 kilograms. That is about 2,260 pounds, because we don't think in kilograms.
I know, I haven't seen most of you in a while.
So first, let's think about the Perseverance rover while it's on the surface of the Earth. So before it was launched out into space to rove Mars for signs of life. So the mass of the Perseverance rover itself is 1,025 kilograms. To give you an idea, that's about 2,260 pounds. So on the surface of Earth, we know that the acceleration due to gravity, or G, is equal to 9.8 meters per second squared. In order to calculate the weight of the rover on the surface of Earth, I would use my weight formula, which is weight equals mass times G. If I plug in all of my known values, I find that the weight of the rover on Earth is equal to 1,025 kilograms times 9.8 meters per second squared, which is equal to 10,045 newtons. That means that the Earth's gravitational pull is pulling with a force of 10,045 newtons magnitude towards the center of the Earth. Now let's think about this adorable little cat as he sits on the surface of the Earth. So we know again, we're on the same planet, my location hasn't changed, so G will remain constant at 9.8 meters per second squared. Now to calculate the weight of the cat, I would do the same thing. Using my weight formula, I would find that the cat's weight is equal to 6 kilograms times 9.8 meters per second squared, which is equal to 58.8 newtons. Now we can see, because of the very, very different mass between the rover and the cat, gravity, the Earth's gravitational pull, is only pulling on the cat with 58.8 newtons of force. Very, very, very small compared to the 10,045 newtons that is being pulled on the rover. Again, this is because of the mass of those two objects. We know that the Earth is going to pull much harder on the more massive rover. Now let's look at what happens to weight if we go from one planet to another, where we know my G, my acceleration due to gravity, will be different. So now let's think about my Mars rover, which we know again has a mass of 1,025 kilograms. So we've already calculated this on Earth, so as a quick reminder, we know that on Earth, the gravitational pull of the Earth is pulling on the rover with 10,045 newtons of force. Now, once this rover is shot out into space, landed on Mars, and is roving the surface for signs of life, let's see what the force of gravity on the rover is there. So on Mars, the acceleration due to gravity, or g, is equal to 3.72 meters per second squared. So you can see that it's about a third of the acceleration due to gravity on Earth. What do you think that's going to do to the weight? Well, it's pretty simple mathematically. If weight is equal to mass times g, and I decrease my g, I'm certainly going to decrease the weight or the force of gravity on the object. So the weight of the rover on Mars is equal to 1,025 kilograms, because the mass of the rover does not change, times 3.72 meters per second squared, which equals 3,813 newtons. If we compare, we can see that on Mars, gravity is pulling about a third as hard on the rover, meaning that the weight of the rover is about a third of the weight of the rover on Earth.